here. And started from the current slide here. Bless you. Now, we got the projector coming up finally. Last time we talked about the trapezoid rule. What we're doing in Chapter 8 is integration techniques and improper integrals. We're just going to focus on integration techniques. And 8.6, the one we're in now, is numerical integration. And we mentioned and talked about and did some with the trapezoid rule last time. Now we're moving to a better rule, the Simpson's rule. Now, this book takes a different approach from most of the others, but basically they both take almost you're getting to the same point, but they get it there different ways. Most other texts I've taught from, either before or after they talk about trapezoid rule, they'll mention another one which is called the midpoint rule. Now the midpoint rule seems a lot like the trapezoid rule. In fact, it is fairly similar. Let me see if I can get a picture here. This was the trapezoid rule. You know, let me get my pen set up. Okay. You see that trapezoid here undershoots the graph there. The midpoint rule would take the midpoint of this interval and do a tangent line there and there. And that would then overshoot, but not quite overshoot as much as the trapezoid rule undershot. I don't have mine quite as a tangent. Got it too high on the right-hand end and too low on the left-hand end. But it's a better approximation than the trapezoid rule. But the thing that makes it a little more awkward is you have to calculate the midpoints and the function at that value, not the ones at the ends, at one of the endpoints. So this book doesn't go into those. Okay? It jumps right to Simpson's rule. What Simpson's rule does is combine the trapezoid rule and the midpoint rule to come up with an even better approximation. So here is the foundation. Now, when we finally get there, some point, there we go, to Simpson's rule. Before, you can think of the trapezoid rule as being a linear approximation. What Simpson's rule is kind of like a quadratic approximation. And since it's a curve anyway, you figure a quadratic's going to fit a little bit better. And a quadratic requires 3 points, where a linear only requires 2. So you're basically guaranteed 3 of the points are going to match, not just 2 of them. So it is going to be a better rule, and it's already a curve, all that kind of stuff. Now, so think of this. What I just described is the trapezoid rule, 2 points. Midpoint rule was a point in between. Hey, guess what we use? Those 3 points, or something like those 3 points. So one way to view the trapezoid approximation of a definite integral is to say that each subinterval you approximate out by first degree, there it is, linear polynomial. And in Simpson's rule, you take this procedure one step further to approximate using second degree polynomials, parabola type shapes. Before presenting Simpson's rule, consider the following theorem for evaluating integrals of polynomials of degree 2 or less. Polynomials of degree 2 or less. That is quadratic since linear. That's all we got. Well, it costs us, I guess. Okay? So here is evaluating an integral of this form. P of x is equal to ax squared plus bx plus c. That's your P of x. Okay? Then, to integrate P of x between a and b, wow. Okay, where did that come from? All right. Goodness gracious. Where in the world did they come up? Well, let's see. P of A is plugging in this value. And you'll have capital A times little a squared plus B times little a plus C. P of B would be capital A times B, little b squared plus B times little b plus C.
Are you saying like the A's and the B's to be capitalized in the like P of A?
What's that?
What's the problem?
Where did that come from? They just made it up, it seems like. But I think there's reality to it. And what it is, they're doing just sort of what I just said before. They're taking the first endpoint from trapezoid rule, the last endpoint from trapezoid rule, and the midpoint, A plus B divided by 2, that's the midpoint, and doing P times that, but then saying 4 times that, without really telling you why, but that's going to be the case. Now, let's calculate this one. I know it's a pain in the neck, but let's do it. P of A plus B over 2. That would be A times A plus B over 2 squared plus B times A plus B over 2 plus C. Okay. Now, that would be A times, this would be A squared plus 2AB plus B squared, that's A plus B squared, over 4, plus B times A plus B over 2 plus C. Okay, if you split these out, this will be an A times A squared plus 2AB times A plus B squared wait, I put the A, I did the wrong A squared. Okay, sorry. Little a squared times capital A, okay, plus 2AB times capital A plus B squared times capital A, and that's all over 4 plus little ab plus little bb over 2 plus c. Oh, what a mess this is. Okay. So those are those terms. And then you do the P of A, which will give you capital A little a squared plus, okay, so let's add to that P of A, which is capital A little a squared plus 2 plus B little a squared, little a plus C, that's a capital B, and then we're going to add to that the P of B, which is plus A times little b squared plus capital B times B plus C. That's the part inside the parentheses there, the brackets. Inside that, this is up here. Now what we need to do is to deal with our denominators and I still don't see how this is getting much better. I think what we have to do is just take the word that's true. Here's the theorem, that integral, when that is your quadratic function, then the integral of that is this weird combination of these things.
And your last word question, because it's being multiplied by 4 there.
Yeah, I mean, that has a little bit of the, oh yeah, right, you're right. I didn't multiply that by 4. Thank you. That will wipe out the 4 there. That'll make a 2 here, and that will make a 4 here. You're right. Very good. So let's see what we've got now. A squared, capital A, plus 2AB, capital A, plus B squared, capital A, plus 2AB, capital A, little a, capital B, and this is in parentheses, plus 2 little b, capital B, plus 4C, plus A squared, plus capital B A, plus C, plus A B squared, plus B little b, plus C. All right. That helps big time. Okay. Let's look at C's first. 4C plus C plus C, that's going to be 6C. That's the last term. Let's look at our, here's a little a squared capital A, and there's a little a squared capital A. So that gives you 2 of those. 2 little a squared capital A. Okay. 2AB capital A, I don't see any other terms like that, so I'll write that down, plus 2 little a little b capital A. Here's a b squared capital A, and there's a b squared capital A. So that's going to be plus 2 b squared, oops, wrong one, little b squared capital A. Can you read that?
Yes, sir.
Black on red. Okay. Little b squared capital A. Get out of there. Okay. So I've taken care of this one, that one, that one. Plus 2 little a capital B. 2 little a capital B.
Right there.
Huh?
There's a capital B little a. It's like big A little a squared plus capital B A.
Okay. Oh, okay. I see this one.
Oh. So yeah, that was there.
Two little a capital B. And there's 1 little a capital A. That makes 3. Okay, I knew I had to have another. Plus 3 little a capital B. So that's that one. And you got 2 of these and 1 there. That makes 3 of those, plus 3 little b capital B's. Okay, so we got those. I took care of that one. B little a. Yeah, we got that one and that one. So that's all of them. Now notice everything's divisible by 2. No, it isn't. You got 2 3s there. So they're going to pull out a 6. Okay? Because your biggest thing here is a 6. Biggest coefficient is 6. And okay. At least now it looks like it's possible. Okay? What they're going to do is okay. That's the part in here. Now we haven't done this part yet, but I'm going to tell you what this is. Remember the mean value, is it mean value theorem or something like that? B minus A is the length of that interval. This over 6 represents the average value of that, and the thing in the integral here is the same as the average value. And so that's what they're doing here. They're getting this to be the average value, this thing over 6 times the length. So that gives you the rectangle that approximates that curve. Okay, that's where it's coming from. Okay, I don't want to show you how to get there because it's it's messy. It's really messy. But that gave enough insight. That's where it's heading, I think. Okay, so anyway, there's the theorem. All right. To develop Simpson's rule for approximating a definite integral, you again partition the interval a to b, inclusive, into n subintervals, each with a width of, guess what? B minus a divided by n, just like we did before. Okay? And that looks a lot like what we had there, except the n would be 6, but that is always for 6. This time, however, n is required to be even. And the reason for that is the subintervals are grouped in pairs so that you always delineate between, so that therefore the n has to be even. Before it didn't. For a trapezoid rule, it didn't have to be even. Any subinterval would. This time you just have to have an even subinterval. So what we're going to do, we're going to do an approximation between these two, x of 0 to x of 2, between x of 2 and x of 4, x of 4, x of 6, x of n minus 2 to x of n, and the x of n, of course, is going to be v and the x of 0 is a. Now, each double subinterval, okay, x of I minus 2 to x of I, so x of 0 to x of 2, x of 2 to x of 4, they differ by 2 there. You can approximate f by a polynomial p of degree less than or equal to 2. So you could do a straight line if you wanted to. You could do a horizontal, I mean, if that fit, or you can do a parabola. Okay? It's just an estimate anyway. Okay? Approximate f by that. Okay? Now, for example, on the subinterval 0 to 2, you choose a polynomial of least degree passing through the points, and here's right. Bottom part of the alphabet doing okay. Top part's completely missing. Okay. Choose a polynomial of least degree passing through the points x0, y0, x1, y1, and x2, y2. Okay? Now, here is, really expanded this, x0, x1, x2, there's a point y0, y1, and y2. So you have 3, this is your function that you're trying to integrate. Now, here is the second degree polynomial that you're approximating that area with. Okay? Now the area we're really interested in is the area under here, which would be pink if you weren't covered with blue here. Okay? So this would be pink all under here, including that little bit. So you see this polynomial overestimates here, but underestimates there. So that should be a better fit than a regular old trapezoid going from here to there. That wouldn't be a very good fit at all. Okay? So there is your estimation. Certainly not exact, it's an estimate. Okay? Now, the integral of this p, this is your polynomial here, from x0 to x2, that's what we see here, from here to there, that's the blue curve, the blue area under that curve. That's approximately equal to the integral from x0 to x2 of f of x. Not exact, but it's approximate. That's just showing it to you. Okay. Now, using p as an approximation of f on that subinterval, you have by theorem 8.4, the one we just did. Yeah. Okay. Here was your f, that's approximately the p, and that 8.4 we did before you came in, Brian, is x0 minus x1, that was your b minus a over 6, times this. Okay? Where this is p as x0, 4 times the p at the point in between x0, this is x1, basically, and then this. Well, that's just 4 times px1. That's what I just said. Okay? Now, what else did they do here? Rather bizarre, but they did it. Remember, may not remember because you weren't in it. Your interval here was b minus, the length of any interval is b minus a over n. Okay? You got two intervals here, x0 to x1 and x1 to x2. So 2 times this is going to be that value divided by 6 that you got from here. And then this you just do p of, this is just x1. It's the midpoint between x0 and x2. Okay? So what we have here, if you clean this up a little bit, 2 will go in the 6 3 times, so you have b minus a over 3n, where n is the number of intervals we have, times this p of x0, which is exactly the same as f of x0. Remember, the p of x0 is here, f of x0 is there. Same point, p of x1 is here, f of x1 is there. P of x2 is here, that's the gray line, and f of x2 is there. All three of those are the same. So we go back, and instead of p of x0, you do f of x0, f of x1, and f of x2. Same values, okay? In between they're not the same value, but those 3 points they are. So this gives you an approximation for the integral from that. Repeating this procedure on the entire interval a to b produces the next theorem. All right, here's what's going to come next. Between x2 and x4, you're going to have another x2 in it, so that's going to give you 2 of those. You'll get 4 x3s, because you get 4 x1s here, and then you'll get an x4. Then you do it again, you'll double the x4, you'll do 4 times x6, x5, and 1 x6. But then when you do x6 to 8, you get another x6, 4 x7s, and 1 x8, until you get to the end, and then you have only one f of xn, which is your b value. Okay, f of b. So here's the next theorem. F be continuous on this interval a to b, let n be any even integer. Simpson's rule for approximating this function that you might not be able to evaluate, period. It may not be integrable, but you can plug in values for it, but it's just not integral. So then this function from a to b of this would be approximately b minus a over 3n. That was the comment. And then your f of x0 one time, at all your odd x's 4 times, at the other even x's 2 times, except the last one is another 1 time. So your first point and your last point, 1 weight. Your odds, you have 4 weights, and then the other evens, you have 2 weights. One from one interval and one from the next. Moreover, as n approaches infinity, the right-hand side approaches that. Okay? So as you let the n get larger and larger and larger, that's Simpson's rule. Okay. Now, here's example 2, using Simpson's rule. Hopefully you'll find it easier to use than to blah, blah, blah about it. By the way, example 2 is also located at larsoncalculus.com, an interactive version of that type of example. So we're going to integrate, and were you here last time? You were, weren't you? Okay, remember we did the integral from 0 to pi of sine. Okay, and do you remember what it came up to be? We did trapezoid rule, and it looked like it was getting close to 2, and I actually did the integral, and we saw it was exactly 2. So let's see how close to 2 we get here. We're going to compare the results for n equal 4 and 8. Last time we did it, let's see if I can find it, we did 4 and 8 for the trapezoid rule. So we're going to wind up comparing these. Okay? So, Simpson's rule, again, is b minus a, that would be pi minus 0, that's just going to be pi, divided by 3 times n, so the first one's going to be 12. See, divided by 3n, in our first example, n is equal to 4, so that's 12. Times, okay? Now we got 4 subdivisions here. That would be at, of course, 0, pi fourths, pi halves, 3/4 pi, and pi. Okay, that's our subdivision. So this is your F0. It's going to be 0. Okay, because sine of 0 is 0. Okay, plus, remember this is 4 times. The odd ones here are 4 times. 4 times the sine of pi fourths. Sine of pi fourths is root 2 over 2. Okay? Plus 2 times the sine of pi halves. The sine of pi halves is 1. Right? Follow it? Okay. Plus 4 times again the sine of root 3 over 2 is, again, root 2 over 2. 3 pi over 2 is root 2 over 2. 3 pi over 4, I can't talk, okay, is the sine of 3/4 pi is root 2 over 2, okay? And then at pi, it's 0 again. So that's another 0. All right, let's see what we get here. This is 2 root 2 plus 2 plus 2 root 2. Okay? So that's going to be 4 root 2 plus 2. So it's pi 12ths times 4 root 2 plus 2. I don't know if this is helpful or not, but that would be pi, if you factor out a 2 here, pi 6 times 2 root 2 plus 1. Okay. Pull out your handy-dandy calculator and see what that gives you. Pi 6 is going to be just a little bit less, no, more than 1/2. So that's going to be a little bit more than root 2 plus 1, so it's going to be 2.1 blah, blah, blah. I think 2.14, 2.15 maybe, I don't know. Did you do it? Okay. I'm doing mine in my head, so I may be way off. Yes, good. So that's approximately 2.00, what do you say? 455. Okay. Okay. They put in the book 2.005. Okay. Hey, think back to the last one, 1.896, and even with n equal 8, we were only up to 1.974. We're already closer to 4 than we were with the trapezoid rule at 8 intervals. More intervals, the closer you get. So this is doing really, really well. Okay? Now, the only difference when you go to n equal 8, well, there's a couple differences. First, you interject pi 8ths in here, 3 pi 8ths, or 3/8 pi, 5/8 pi, and 7/8 pi. Okay? Now, I can't do those in my head, so you're going to have to. And the other thing it changes is your initial value is going to be b minus a, again, is pi, divided by this time 8 times 3, which is 24. So this time it's going to be pi 24ths times. The 0 is still going to be 0. You know, evaluated at 0 is still going to be 0. But this time your 4 is going to be here. So it's going to be 4 times the sine of pi 8ths. So keep your calculator handy. Plus 2 times the root 2 over 2. That was pi 4ths. I could do that. Plus 4 times the sine of 3 pi over 2. Plus twice 1. Because sine of pi halves is 1. Plus 4 times the sine of 5/8 pi. That's your root 2 over 2 again. Twice that is just your root 2. Okay? Plus 4 times the sine of 7/8 pi. Okay, that's supposed to be an 8. Okay. And then the last one's going to be a 0 anyway, so I'm not going to write it down. Now, if you want to save yourself some grief here, just a little bit, not a lot, you know that this value and that value are the same. So you can just do 8 times this one. Okay? Pi over 24 up front. You can wait and do that at the end if you want to. So 8 times sine of pi 8ths plus 2 root 2, because those two are the same, plus 8 times, that's 3/8, not 3/2. And sine of 3/8 pi is the same as sine of pi pi, so it's going to be plus 8 times the sine of 3/8 pi. That will take care of this one too. Then plus 2, that's only there once. Okay. Whatever that sums up to, multiply it by pi, divided by 24. I know it's messy. You want me to talk through it again?
Yes, sir. I was confused on where the
What's that?
I was confused on where the pi over 12 is coming from there.
Okay, this one up here, which is here. Okay, Simpson's rule is b minus a over 3n. Okay, your b is pi and your a is 0. So that's where the pi comes from. pi minus 0 is pi. 3n, for the first example, n was 4. 3 times 4 is 12. Second example, n is 8. 3 times 8 is 24. So that's where the pi 12 came from here, the pi 24. Okay? That's just Simpson's rule. But it came from that same b minus a over 6, which was 2 times 3. Whatever. Now, and again, to make your life easy, we already discounted the 0 and the pi because sine is 0 there, so that didn't add anything. But it's 4 times sine, but it's actually 8 times sine of pi h, because whatever sine is on this side is the same on that side. Okay? So it's 8 times sine of pi h plus 2 times root 2 plus 8 times sine of 3h pi plus 2. End it there because you took care of the others. And then multiply that by pi and divide by 24.
So where is our under x1? That's all the like the pi over 8, 3 pi over 8.
Yeah. So where did they come from?
But I mean that's like our x.
Those are the intervals, right? When you did by 4, it was 0, pi fourth, pi has 3/4 pi and pi. Those are your splitting 0 to 8 in 4 pieces. If you do it in 8 pieces, then you get one in between. 0 pi h, pi fourth, 3h pi. Pi has 5h pi, 3/4 pi, and 7h pi and pi. But the value, sine at those values, these two are 0. And because sine is a very symmetric curve, the sine of pi h is the same as the sine at 7h pi. And the sine at 3h pi is the same as sine of 5h pi. And we already took care of, we knew these two were the same, root 2 over 2, so we just doubled that. And it was down here, I said 2 times root 2. One from here and one from here. But this one line in the middle, it only shows up once. You multiply 2 by it because Simpson's rule has a 2 by that. So did you punch it on the calculator? Oh, I thought that's what you were doing. All right. Now, you want me to talk through it while you punch? Okay. Let's start with the bracket, and then we'll come back and do this. It's 8 times the sine of pi h. So it's 4 from here and 4 from there. 8 times the sine of pi h. You doing it?
I probably can't do it.
What's that?
I probably can't do it.
I can't.
Oh.
Oh, it doesn't have, okay. Okay, well, you don't have to do it. I'm just going to make you feel warm and fuzzy about it. I think he intentionally didn't bring a calculator. He never gave him one, so you just ruined his day. Okay. All right. Start over. Be sure you're in radian mode. Okay. It would be terrible if you're in degree mode. Okay. 8 times the sine of pi h. Always fun with a new calculator, trying to find where the keys are.
I'm trying to find
The pi.
Shift and this.
say pi.
Yeah. 8 times the sine of pi h. Got it. Plus 2 times root 2. Got it? Plus 8 times the sine of 3/8 pi.
No,
times the sine of 3h pi.
This 8 sine.
3h pi. 3 pi divided by 8. 3 times pi divided by 8. The sine of that, right? Plus 2. Got all those? Plus 2. Stop right there, because we already did the others. Okay? Then, multiply that answer by pi and divide it by 24.
I got 2.0.
Okay, wait. Call it out to me.
2.00026.
Okay. Wow, that's much closer to 2. Okay? You're within 4 significant digits. Yeah, okay? You're really close to 2. Okay. So Simpson's rule does zoom in faster, much faster than trapezoid rule. Okay? They got 2.00, 3 zeros and a 3. Good deal. All right. That was our doing it. Let's see how they do it. All right, to erase, or you want to leave it on a little longer? Oh. Whoa. There. What's that? Okay. All right. Oh, I needed to erase it first. All right to erase? Okay. All right. So when n is equal to 4, you have this interval being pi over 12. Remember, that's what we got. It's pi minus 0, that's the pi, over 3n, and n is 4, so that's 3 times 4 is 12. Times the sine of 0, which is 0, plus 4 times the sine of pi fourths, plus 2 times, remember, your Simpson rule coefficients are 1, 4, 2, 4, and then whatever the last one is 1 again. So it's 4 times sine of pi fourths, 2 times sine of pi halves, plus 4 times sine of 3/4 pi, plus sine of pi. But you know sine of pi is also 0, so we left that one off. And we already know sine of pi fourths is root 2 over 2. And 4 times root 2 over 2 is 2 root 2. But that's the same for here, so that's 4 root 2, and this is just 2 times 1. So 4 root 2 plus 2 times pi divided by 12. And they claim that comes out to be 2.005. Really close to 2. Much closer than trapezoid rule at n equal 8. Twice as many intervals, but you're already much closer to the answer. Now, all right. For n equal 8, you have, they didn't show you what you had. They just said this comes up being that. Now, the only difference is, because n is equal to 8, it'll say pi minus 0 is pi, divided by 3 times 8, which will be 24. So that comes up pi over 24 out front. Still the sine 0, which is 0. This time you have 4 times sine of pi eighths, 2 times sine of pi fourths, 4 times sine of 3h pi, 2 times the sine of pi halves, 4 times the sine of 5h pi, 2 times the sine of 3/4 pi, 4 times the sine of 7h pi, and then you have your sine pi, which is 0. So you have more things here, a little bit bigger coefficient, but what we did for funsies, the 4 times the sine of pi eighths is the same as sine of 7 pi eighths. Just happens to be going up and coming down the same value. And downwards here. Okay. And so that made our calculations easier. Throwing out the sine 0 and sine pi because those are zeros. And then 4 times sine of pi eighths was, sine of pi eighths is the same as sine of 7 eighths pi, so we just did 8 times that one. This was already a 2 times this, so that's just 2 times 1. Oops, I left off mine. 2 times sine of pi fourths. That was 2 times root 2 over 2, which is just root 2. Then you had the 3/8 pi, 4 times the sine of 3/8 pi, but make it 8 times it because that's the same as 5/8 pi, sine of 5/8 pi. So you did that one times 8. Then 2 times the sine of pi halves, and you got it 9. Sine of pi halves is 1. So just a 2 there. Add all those up, multiply by pi, divide by 24, and you got 2.0003. Okay. Much, much closer.
And so our ends will always be 2, 4, 6.
Have to be
8.
even. They have to be even. N has to be even. Yeah. For Simpson's rule. For trapezoid rule, it doesn't. But for Simpson's rule, it does. All right. Now we move to error analysis. I don't want to spend a lot of time on that. When you use the approximation technique, it is important to know how accurate you can expect the approximation to be. The following theorem gives the formulas for estimating the errors involved in the use of Simpson's rule and trapezoid rule, and as you should expect, the errors for Simpson's rule is going to be a lot less than the trapezoid rule. We saw that. Let's see what it turns out to be. If f has continuous second derivatives on a to b, and sine certainly would do that too, then the error, E, in approximating this integral by the trapezoid rule, the first one we did, okay? Here's what the error will be. Absolute value of the error is going to be less than or equal to, this will be the greatest it could be, b minus a, in our example it was pi minus 0, cubed, okay? So a bigger interval, you expect to have a bigger error. Divided by 12 n squared. Ha! The more intervals you have, the error goes down really, really fast. And we saw that too. Times the maximum value of the absolute values of f double prime on that interval. So what we would do in this case, your function was sine, your first derivative was cosine, and your second derivative was minus sine. We'll take the absolute value of it. What's the maximum value there? 1. Okay? Because sine stays between, on that interval, between 0 and 1. So the maximum would be 1. So that's what we would use, which wouldn't contribute anything here, just multiply by 1. Okay? So that would be the error bar there. So let's just figure out what it is. This would be pi. On the one we just did, it would be pi cubed divided by the first trapezoid rule we did was 12 times n was 4, so that would be 12 times 16. So pi cubed divided by 12 times 16 times 1. So see what that came out to be. Pi cubed divided by 12 times 16. Okay, 0.16. Remember, that one came out 1.986. That is, the error is less than 0.16. Yeah, less than that. So that, yeah, that fit. Now do the same thing, still the pi cubed, but this time divide it by 12 times 64. That was when we did 8 pi cubed divided by 12 times 64.
.040.
0.040, we came out 1.974, which is less than 0.04. Yeah, got it. All right. Moreover, if f has a continuous fourth derivative on a to b, fourth derivative now on a to b, then the error, e, in approximating the function by Simpson's rule, the absolute value will be less than b minus a to the fifth power, so that makes the numerator even bigger. But look at that denominator, 180, that's a bigger number down here, so it's going to be a smaller error, but into the fourth, raised to the fourth power, and the maximum of the fourth derivative. Now, our derivatives before, remember, it was a sine function, right? And the derivatives, whatever they are between sine and cosine, absolute value of that is 1. You know, the maximum you can get is 1. So that's just going to be a 1. So let's plug in the numbers we had there. This will be pi raised to the fifth power okay, divided by 180 times 4 to the fourth power. I don't want to figure out what that is. Let's see. 4 squared is 66. I don't know. I think it's 256, but I'm not sure. But your calculator will do that, okay.
Okay, it gave me a big number times 10 to the negative 3, so that means there's 3 zeros out in front of this.
Right. Mm-hmm.
So it was 6.641. So it'd really be
Times 10 to the minus 3.
yes,
So that would be 0.006. Blah, blah, blah. And sure enough, ours came out to be 2.005. So we were within that. Okay. I'll do it. Pi to the fifth power divided by 180 times 8 raised to the fourth power. I'm not about to do that.
now we're times 10 to the negative 4, 4.15.
So it's 0.0004, and we were at 2.0003. So yeah, within that. Okay, because that's maximum error. So you see, yeah, Simpson's rule gets small way faster than the error gets small way faster than it does in trapezoid rule. Okay. Here's an in general I don't see in the book, so I'll just read it here. In general, when using an approximation, you can think of the error as the difference between the function and the approximation, which is basically what we do. Theorem 8.6, that was the error one, states that the errors generated by trapezoid rule and Simpson's rule have upper bounds dependent on the extreme values of your second derivative for trapezoid rule and fourth derivative for Simpson's rule in the interval from A to B. You have to stay within that. Furthermore, these errors can be made arbitrarily small by increasing the n, provided the f double prime, f fourth prime are continuous and therefore bounded always on A to B. All right, good deal. Any questions?
So
yeah,
f prime is your continuous.
What's that?
I said f prime is your slope through the thing.
Yeah, right.
F double prime is your
second derivative of that derivative,
which is you're like
the concavity.
Yeah, right.
Right. And then f triple prime would then be the derivative of f double prime. F to the fourth prime would be the fourth derivative would be the derivative of the third derivative. Right.
Well, what do the third and fourth derivatives tell you?
The third one tells you, strange word, jerk. Okay. And the fourth one, I can't remember if I've ever heard a name for that. It just, huh?
What is the jerk?
It's how rapidly the concavity is changing, basically. And I don't know why they name it jerk. Maybe the guy who came up with it. No, never mind. Okay.
Nobody liked them.
Nobody liked him. So, I don't know. You're sick in the mind. Okay, let's do example 3. This is a different one. Determine a value n such that the trapezoid rule will approximate the value of the integral from 0 to 1 of square root of 1 plus x squared dx with an error that is less than or equal to 0.01. Okay? Now, in order to determine this value of n, this error is going to be your error bound. So let's figure out what that is. For trapezoid rule, it's, I can do the b minus a, that's 1, right? b minus a, that's 1. 1 over 12 times n squared. I really don't need the parentheses there. I don't know why I put them in. Let me take them out. They're not contributing anything, so they just are extra messes on the board. Okay? Now, the other thing we need is the maximum second derivative of this function on the interval 0 to 1. Okay? So let's do that. I don't like taking derivatives of radicals. So how would I write that function? 1 plus x squared, is that what you said? To the what? No, 1/2. Negative 2 is 1 over squared, right? Okay. So there's your, so let's do first derivative. What would that be? 1/2 of 1 plus x squared to the negative 1/2 times, chain rule, 2x. Okay, so I'll wipe out the 2's there, and that, written in a different way, would be x over 1 plus x squared, square root of 1 plus x squared. Not that that's how I want to leave it. Okay? I actually like the way we have it here, which is x times 1 plus x squared to the minus 1/2. All right, so I need to take a second derivative of that, f double prime of x. Now we got a product rule with the chain rule on part of it. Okay? So you tell me how this goes. Anybody? Help me. Somebody help, please. I'm drowning. Okay, you're going to take the root of the first times the second. 1 plus x squared to the minus 1/2. There's the first time, the derivative of the first times the second. Okay, plus x times negative 1/2, 1 plus x squared to the negative 3/2 times 2x. Okay, let's see if we can write that in any reasonable kind of form. This will be 1 over the square root of 1 plus x squared. Right? That's the first one. Plus, now let's get our numerator materials together. In fact, it's not going to be a plus, it's going to be a minus. Right? Because there's a minus right there. Okay. All right. First thing I'm going to do is cancel out the 2's, so I don't have to worry about them. So here we have an x in the numerator. Nope, an x squared in the numerator. X from here and an x from there. Okay, and the denominator it looks like the square root of 1 plus x squared cubed. That's what it means to 3/2. Okay? Now, I'm going to make a little guess here. I don't know if this guess is educated or just a guess. Okay? I'm going to guess the maximum value is going to be at one of the two endpoints. Okay? Otherwise, I have to take a derivative of this thing and see where it's equal to 0. I really don't want to do that. Okay? Not today. So let's just see. One endpoint where x is 0, what is this value? When x equals 0, this is 1 over 1. So that's 1 minus, and that would be 0. I have a feeling that's not, but it may be. So we'll just call that 1. Okay? It is 1. On the other end, where x is equal to 1, what do we have? This will be 1 over the square root of 2, right? Right? Okay? Minus 1 over the square root of 8, I think it is. Yeah. Okay. All right. Which is going to be 2 root 2. So let's make this 2 minus 1 over 2 root 2, which is 1 over 2 root 2. Is that right? I think I did it right. Square root of 8 is 2 root 2, and then this would be 2 over 2 root 2 minus 1 over root 2, 2 root 2, which would be 1 over 2 root 2. Well, I may have been wrong. That's a smaller number than this one. Now, I don't know for sure if that's the max, but let's just say it is for argument purposes. That 1 is the maximum second derivative there. The other one's going to be something less than 1. Okay? So we'll use 1 and hope we're okay with it. All right? So, what was the error for Simpson's rule? 1 over, in this case 1, over 2 times the maximum, which is just going to be 1. So basically it's going to be that. So, oh, okay. Let's write this down. 1 over 12n squared, that's the error, is less than or equal to 0.01. Okay? What we're going to do, multiply both sides of the equation by 12n squared. Right? So this would be 1 is less than or equal to 0.12 n squared, right? So divide both sides by 0.12, and n squared has to be greater than or equal to 1 over 0.12. So you figure out what that is.
8.3.
Okay, 8.3 something. Okay, take a square root of that. N is greater than or equal to
2.88.
Let's say 3, because n's got to be some number. Now, that seems awfully small to me. They said 2.89, so we choose n equal 3. That should get us within an error of 0.01. Okay? Yep, we did it right. Okay. So, if we did the trapezoid rule there, and I didn't know that we had to, all it said is determine the value. We did. They show you what happens if you actually plug that in. You know, you would split that into, oh, why am I doing the talking? I think it shows up here. Can I erase this now? Okay. Everybody? Can I? Okay. So, we did all this. Maximum value on the interval is at 0, and that would be 1. Okay, so by 386, we got it less than that. Okay, and oh, look at how they did it. Yeah, same type principle. They got the same answer, and we'll round that to 3. Okay, it has to be greater than or equal to that, but it has to be an integer. I don't want to do 2.89 intervals. No, I don't want to do that. I want to do 3. Okay. So, Simpson's rule was 1 over 6. Okay, 0 to 1, so 1 minus 0 is 0. And this would be 2 times 3 is 6, so that's where that came from. And then you do the value. This is trapezoid rule. The value of the first plus 2 times the value of the second plus 2 times the value of the third. No. Our interval is 0, 1/3, 2/3, and 1. Okay, so 1 times the value here, 2 times the value here, 2 times the value here, and 1 times the value there. So they did this at those places. So that's 1 plus 2 times the square root of 1 plus 1/9, 1 and a 9th, plus 2 times the square root of 1 and 4/9, okay, plus square root of 2. Okay. If you do that and take 1/6 of that answer, they claim that you get where did they get the 2 values? I don't know. Okay, I think I know. You get some value, you add the error to it, 0.01, and you subtract it from it, and you get that. So they must have come out 1.154, and this is from 1.164 to 1.144. So yeah, it's going to be in between those two numbers. All right. We weren't asked to do that, but they did it. Did you sort of follow what they did? Okay. It makes no sense to me to give it 4 significant digits when your error is 2 significant digits. No, I mean 1.14 to 1.16. If your estimation was 1.15, then you're going to be between that. It makes no sense to do the error to be this digit and you haul around the third digit there that you're not ever going to use. Sort of dumb. Oh, we finished 8.6. Isn't that wonderful? Homework exercises here include any of the odds, 3 to 13. They're all at Calc Chat. 3 is at Calc View. Any of the odds, 15 to 23. They're all at Calc Chat. 17 is at Calc View. Do either 25 or 27. They're both at Calc Chat. 25 is at Calc View. Either 29 or 31. They're both at Calc Chat. 29 is at Calc View. Do 33. Do 35. Do 37. If you can think about doing 39 if you want to. That's completely up to you. All these should be at Calc Chat. I'm not sure 39 will be. 41 should be at Calc Chat. You can do that. And or 43. 45, they say you're going to need a computer algebra system to do, and you might. I don't know. I'll let you work on that one. 47's a proof. You can do that if you choose. All right. Let's see. Oh, they said this came out to 1.154. I'm sorry, I didn't carry this through when you did that calculation. Guess what? If your error is less than 0.01, it makes no sense to carry that 4 out there. 1.15 plus or minus 0.01. That's all you do. There's no reason to carry that third digit because that's outside your error, you know? Yeah. So I would do it, forget that, and forget that. That would make sense because your error is 0.01. So don't carry a digit outside your error. Okay. And that was the last slide in the section. So let's move on from here. How are we doing on time?
25 minutes.
Huh?
25 minutes.
25. Okay, good. All right. We finished that one. And let's move to 8.7. 8.7 should be one of your favorite sections of all time. Integration using tables. Okay. So you don't have to go back and reinvent the wheel and come up with... Did I just close that? I'm afraid I did. Let's try it again. I meant to expand it. Now I hit the wrong key. Okay, that's what I meant to do. Okay, we're still in Chapter 8, Integration Techniques. We're not going to mess with improper integrals. Integration by tables and other integration techniques. Okay? Objectives here, find the indefinite integral. Oh, man. Using a table of integrals. Find the indefinite integral using a table of integrals. Find an indefinite integral using reduction formulas. And we're going to see how they show up in tables too. And find an indefinite integral involving rational functions of sine and cosine. Boy, that sounds exciting, doesn't it? So let's do integration by tables. Many people find tables of integration to be a valuable supplement to the integration techniques discussed in this chapter. Let me suggest a different word here. A valuable substitute to the integration techniques found in this chapter. They just go to the table, find the answer, rather than working out and getting the answer. Okay? Well, I don't know. I may be overstating that. Tables of common integrals can be found in Appendix B. It's a pretty limited table. I kind of wish I had brought up my CRC manual. That's Chemical Rubber Company is what CRC stands for. They used to publish every year. I doubt if they do anymore, but they still may. An enormous volume of, it's not quite that thick, about that thick. And the paper is onion skin thin. Okay, so thousands of pages in that big old book there. And they have all kinds of math stuff, all kinds of physics stuff, all kinds of chemistry stuff, just about anything you could want to know in those three fields, math, science, physics, and chemistry, can be found in those tables. Okay? And they're integrals tables and differentiation tables, whereas the one in the book may get up to, I don't know, 100 integration tables. Get up to 100. I was just guessed at it. I'm guessing theirs goes into several hundreds anyway, and maybe into excess of 1,000. So they have way, way, way more. Okay. So integration by tables is not a cure-all for all the difficulties you can encounter with integration. Using tables of integrals requires considerable thought and insight and often involves substitution. So you still will be using your techniques. Each integration formula in the Appendix B can be developed using one or more of the techniques that we studied here. They just done the work for you, put it in the table so you can just look it up and use it rather than having to do all the work. Okay? but there's an art to using the table. For instance, Formula 4. So basically what you're doing here is going back to the table. Formula 4 is the integral of u over a plus bu squared du is equal to 1 over b squared times a plus 1 a over 1 a plus bu plus the log of absolute value a plus bu in parentheses plus c. Okay, that's right out of the table. I want to make sure they got it. It says it can be verified using the method of partial fractions. Okay? And you could go back and do it. Formula 19, I'm sort of picking them at random. That's at the top of the next page. The square root of a plus bu over u du, that integral is 2 times the integral of the square root of a plus bu plus a plus the integral of du over u times a plus bu. Okay? Well, guess what? That still has an integral in it. Okay? Now, you do that, you get to there by integration by parts, but then to get the second integral there, ooh, no you don't. Huh, they just leave it there. And then you have to basically go and find something that looks like that in the table to do the second integral. So that's it. Like I said, it's a process, almost an art. Formula 84, that's at the sort of the middle right-hand column of the next page, is the integral of 1 over 1 plus e to the u du is equal to u minus log of 1 plus e to the u plus c. And that said can be verified using substitution. So, yeah. Do with that. So, see, all these use the techniques we just did, some more than once, and hopefully you can follow this through now. I just realized I left this on the board way too long. Sometimes when you leave it too long, you get all the race. But fortunately, it's not with a little bit of elbow grease, this is erased. If you leave it up too long, you'll have almost a permanent message there. I didn't want that to happen. See that green? We didn't want that too. Most of these other marks. I'll say semi-permanent anyway. If I get Windex, it can get most of that off. Okay. Sorry. Okay. So we sort of skipped some stuff here. I'm sorry I wasn't noticing. Let's go back. This is a decent little review here. I wasn't paying attention to the book. I was just looking at the slide. This is a review. Okay. Integral of x log x dx. Okay. Without using the table, how would you do that? A little bit of review here. It's kind of the undoing of the chain rule a little bit in a sense. Actually, more an undoing of the product rule, but there may be a little bit of chain rule activity in, but mostly product rule.
Well, we're not seeing this because if we The first part would be x squared over 2.
Okay, if you are integrating that, okay, and that is an integral sign. But anytime you have a product of things, sort of think integration by parts. You're going to split the parts up, do one integration, one a derivative, okay? Remember how that went? You pick a u and a v, a u and a dv, okay?
Oh yeah, and then you have on the other side would be dv over u or
Right.
v over u.
Right, yeah, okay. So, in this one, let the thing you're going to take the derivative of, surprisingly here, you make it the log x. Okay? I forgot to write my u in there. Okay, duh. I said it, but didn't write it. Okay? Let u equal log x, and dv equal what's left? X dx, okay, because the d's always go together. Then on this one, you differentiate. Then du is equal to what? Good review of derivatives. What's the derivative of log x?
Is it 1 over 6?
1 over x dx. The d's go together, remember? This one over here, you integrate. The integral of dv would just be v, and the integral of x would be, and this is what you were saying,
So it's x squared over 2.
x squared over 2. Now this one, you don't put the plus c's. Okay, we wait until the end to do that. Okay, don't do it for the intermediate steps. Okay, then what you do, this integral up here, this is a result of the product rule. The product of these two, so this is equal to the product of these two, which would be x squared log x over 2, minus your bottom line here. And that would be a, let's pull out the 1/2 times the integral of x squared times 1 over x dx, right? V du. The 1/2 from the v, the x squared from the v, and the 1 over x dx from the du.
Wait a minute, so it's not du times dv?
What's that? Okay, here's what the rule is for integration by parts. Let me start with this. Let's go over the product rule of a derivative. D of uv, right? Derivative of a product is equal to u times the derivative of v plus v times the derivative of u, right? Okay. What if that was everything was integrated, including this? And what if this is what we have right here, right? What's the answer to that? It would be the integral of the derivative of du. Well, the integral of the derivative is just, this thing right here would be uv minus the integral of v du. Well, that's what we got here. We've got a u dv here, and that is the uv, the product of these two, minus the integral of v du. Okay? The v part was x squared, 1/2 x squared, 1/2 x squared, and the du part was 1 over x dx. So the 1/2 comes on the outside, x squared. Now, that's a pretty easy integral to do, because what is 1 over x times x squared? No, x. Because x goes into x squared x times, right? And what is the integral of x? So you have x squared log x over 2 minus, what's the integral of x dx? You've already done it once. No, integral, not derivative.
X squared over 2.
X squared over 2. Okay. And then you can put your plus c. So this will be 1/2 x squared log x minus 1/4 x squared plus c. And if you wanted to do something different, you could pull out 1/2 x squared and have log x minus 2x squared plus c. You can do all sorts of things to it, but that's what you get. Let's see what they got. X squared over 2 log x, just what we had, minus x squared over 4. They wrote it in different forms, plus c. Okay? Maybe this is not a bad review for the test, is it? Okay. That's integration by parts. If you have a product of things, see if you can split that product, one to be a u that you're going to differentiate, the other a dv you're going to integrate, and then see if that makes it easier to go. Most of the time, you choose your dv to something that gets simpler. This one actually got more complicated. The reason for that, you can't integrate log x, but you can take a derivative of it, and that actually gets much simpler. So this time you did the thing you take the derivative of gets simpler, not the thing you integrate. Okay? Wow. I wasn't anticipating this, but let's go for it. All right, to erase? All right, let's do the next one. Whoa! The integral of log x over x dx. Okay. Now, what would you use for that? The first one was x log x. Now it's log x over x.
Substitution?
Yes, perfect. And what would be your substitution?
Well, see, I'm confused on this one because normally you would want to use your denominator.
In most cases, you want to use that denominator, except this one. Log x sort of throws you off. It did last time, it does this time too. So what would be your u?
U equal
log x. Okay, then du is equal to 1 over x dx. Perfect. Hey, there's your thing. What does this produce?
The integration of
u, not over, u du, right? Because 1 over x dx is du, and log x is u. It's just u du, right? Do you? Never, no, okay. And what is the antiderivative of that? As if we hadn't hit this enough times today.
u to the second power over 2.
Okay, plus c. But now we want to go back and plug in what u is, or u are, and what would that be? Log x squared over 2 plus c. Now, be sure you don't do log of x squared over 2. That's a different thing. It's log of x squared. Okay? The whole u squared. And that's what they have here. Plus c. All right, how about this one? They love these x's and log x's, don't they? The integral of 1 over x log x dx. What you reckon you're going to do with that? Same thing. Same thing you did on the last one. Or let's try it anyway. First try. What was that? U equal log x. Okay? That is the most complicated thing in there because it's in the denominator and it's a log. Then, what's your then part? Got it. Now let's see what we got now. The integral of what?
So it would be 1 over du.
Over u du. Because 1 over x dx is your, this part here is your du, and then log x is your u. So this is your u, and this part is your du, so it's 1 over u du. Okay? Now, what would that come up being? Any ideas? You got it. This is the log, natural log of u, and you probably should put it in absolute value part plus c. But now we go back and plug in what our u is, and what is your, what are your u is your u? Log of? Log of natural log of x. And there's no really easier way to write that plus c. I hope that's what they, yeah. Only.
Go over quick what log and natural log is. Again.
What is it?
Like what is, I mean,
okay.
You know, like what it's.
Okay. I don't know if a graph will help. If you remember what the e function is, it basically is that, right? This is y is equal to e to the x, right? Well, the inverse function of that is the log function. So whereas this goes through 0, 1, this goes through 1, 0. Where this approaches the x-axis asymptotically, this approaches the y-axis asymptotically. So that's the log function. Can't ever be 0, can't ever be, I mean, you can't take the log of 0 and you can't take the log of any negative number, ever, ever. That's why you have to put absolute values around them. So they're always positive, okay? And what the log does for you, it takes really big numbers or really, really small numbers and makes them more usable numbers. If you take the log of a big number, like the distance from Earth to Sun is 93 million miles. If you take the log of 93 million, do that on your calculator.
.968.
Hey, I'll deal with 7.968 way more frequently. I want to live with 93,000,000. It takes a big number and makes it a much smaller, usable, friendly number. Okay.
So then to use that again, though, you'd have to say.
Well, then do the e of that number. Oh, you mean if you took a log of that, like this one's doing?
Well, no, sir. I mean, like to be able.
To get back to your original thing?
Or like, how would you say, like, 7.968 is the distance to the sun,
Well, that's the log of the distance to the sun. So to get the distance to the sun, take the e of that number. Exponentiate that number.
to the.
E to the 9, whatever you said, 7.968 or whatever.
I'm doing something right. I'm getting 2,880.
Woo, wait a minute. E to the, didn't you say 7.968? Okay. Do E.
I must have not been enough zeros last time.
Right, okay. All right. Now do E to the.
18.348. Yeah, there it is. There it is.
So whatever you get as an answer, then exponentiate that, and you got it. So, and that's what is done. Use it in statistics a lot when you have huge numbers you're dealing with. Take a log transform, deal with those numbers, and then whatever your answer is, exponentiate it. That's, okay.
Thank you.
Sure. And there's one more here. Ooh, this one. And this is where you came into problems here. What if you have the integral of x over log x? Which you like better, trapezoid or Simpson? You can't do it. You can't do that using any of the techniques. That's not what they call an elementary function. So you're going to have to do it approximation, a numerical method. You're not going to get an answer with that. Of course, your x can't ever be 0 and your x can't ever be negative, but it can be any other. And by the way, x can't be 1 either, because what is the log of 1?
Doesn't exist.
Nope, it's 0. And you can't divide by 0. Yeah. Okay. So if you were doing with something like that, you could do this interval from 0.1 to 0.9 or something like that. You couldn't put a 0 here. You couldn't put a negative number here. And you couldn't put a 1 here. You could go from, you can't do a 1 here, but you could do a 2 to 7 or anything like that. But your limits here would have to be between, not counting 0, but between 0 and 1, but not counting 1 either. You could do that integral there numerically. Or you could do it from anything greater than 1 to anywhere you want to go. You could do that numerically. But you can't do, can't do it. Just can't do it. All right. Now, okay, they do have another, here, are we at time? Oh yeah, wow, it was fun while we had it. Okay, we'll pick up then, this bottom little bit on page 566. I want to get on to doing these rather than just talking about them, but we're almost there. We didn't get enough done to do any homework exercises here, I don't think. So, yeah, just hang off and we'll get those done next time. Work on anything up to 8.6. All right, when we finish this, I'll have your test ready. I may even already have it ready for you. In fact, do you want to take it now or use the extra weekend? Let me see if I got it run off. What's that? Let me see if I do. I meant to get them done, but I can't recall for sure now if I did or not. This was in the wrong class. 126. All right, here we go. Test 1. Nope, this is the wrong test 1. Sorry, I didn't run them off. Okay, I thought I had, but all right.
Have a good weekend.
You too, thanks.